All right, moving on to number 3. Let's go ahead and plot some more points. And we will connect the dots. Now, if you take a look at this one, it does look very similar to the V absolute value that we did in the previous example, but the sides are not exactly linear. If you were to connect the dots, you would have to curve your pen or pencil in order to connect them. So this is probably going to be our parabola shape. So we're going to be dealing with what's called a quadratic function. And some properties about quadratic functions, we'll go ahead and list domain and range. Now, quadratic functions are U-shapes, so they could be upside down like the one in our example, they could be right side up, and they could be located anywhere on a graph. So no matter what U-shape you draw, if you were to drag your pencil left to right, it would be all real numbers. However, if you were to drag your pencil low to high, it would change depending on where that U-shape is located. So for the range, we'll say changing, but for this particular example, notice how the lowest our graph would go is -infinity, and the highest I can drag my pencil is up to 4, and I can include it. So I'll go ahead and throw in that bracket. Now, since these are not lines on the sides of the parabola, we do not have a constant slope anymore. For instance, the slope between these 2 points would be 1, okay, rise over run, and the slope between these 2 points is 3. So we do have a changing slope. It's that change in slope that's causing the curvature of this graph. So we're not dealing with straight lines anymore. In terms of discontinuities, there are no holes, no jumps, or asymptotes. So we can say no discontinuities. And some other things that we should be familiar with quadratic functions is that we can factor them in some cases. Remember, factoring is where you break down an equation into its individual factors or parenthesis groups that are being multiplied together. Sometimes, though, factoring is not an option, so this is when we can use everyone's favorite quadratic formula. We might not see it a lot this year, but I will guarantee you that we will see it, so we should be familiar with it. The quadratic formula is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now, I know my pen's a little thick, you might not be able to see this, so perhaps rewind and go ahead and listen to the words that I used to help you write down that quadratic formula. Let's go ahead and see if we can figure out the equation of this parabola. We can approach this 2 different ways, talking about the properties and the characteristics that you probably discussed last year in pre-calculus. We can go ahead and take the transformation route by utilizing this vertex, much like we did for the absolute value. Normally the vertex starts at the origin, but notice how this one was moved. It was specifically moved right 1 and up 4. So for this h of x function, based on the transformations, we would need an x minus 1 squared, because it's a quadratic and it moved to the right 1. It also moved up 4, so we'll go ahead and add 4 on the end. And we do also have to be careful, because this is an upside down parabola, we need that negative in front, which causes that flip over the x-axis. So you can utilize transformations to help you with that equation. You could also have used the x-intercepts. Notice how we have x-intercepts at -1 and +3. So those x-intercepts are directly related to the factors of the function. The x-intercept of -1 would be related to a factor of x plus 1, and then the x-intercept of 3 would be related to the factor of x minus 3. Again, we would need to remember that negative out front because our parabola is upside down.